In part 4 of our discussion of Chapter 6, we are going to focus on the Michaelis-Menten mechanism to describe how most enzymes function. So you will hear this often referred to as Michaelis-Menten kinetics. And this is really going to be where our focus is now. Before we move too deeply into a discussion of the Michaelis-Menten treatment of enzyme kinetic data, I wanted to lay out the historical context of the time. And I really want to also emphasize that the advancements made by Michaelis and Menten that we will talk about, these are not made in a silo. These are built upon the contributions of various individuals dating back almost 100 years. So they didn't just come out of nowhere and say, oh, look, here's this thing. In fact, that was built upon years of study of the study of various different biological catalysts. So, okay, let's start from the idea of vitalism. I've talked about this before, but here I'm going to represent it to you so that you are both fresh and also can see how it relates to today's conversation. So, first, vitalism was the theory that the origin and phenomena of life are dependent on a force or principle distinct from purely chemical or physical forces. So what this basically says is that there is a spiritual component that drives certain reactions in living organisms that cannot be described by chemistry and physics. And you can actually date this philosophy back to the time of Aristotle. So Aristotle proposed something very similar, and this was propagated through the years. And so going into the 1800s, the vitalist movement was still very strong. Now, it was often invoked, vitalism and vitalistic explanations were often invoked to explain things that, say, couldn't readily be explained by chemistry and physics of the time. And this was really kind of problematic because it in some cases was used just as sort of a catch-all explanation for things that were not understood. And what was becoming increasingly aware, or what popular, let's say, was basically to just, if you couldn't explain it, let's say, oh, vitalistic forces, that's what's responsible, and there you go. Now, in the mid-1800s, so think 1830s, 40s, and 50s, classically trained organic and physical chemists were starting to push back against vitalism. They were starting to really try to test the limits of the vitalistic force that had been really invoked so frequently up to that point. And what the philosophy of the opposing camp here, the non-vitalistic camp, what their philosophy really was that it wasn't so much that there is a spiritual or vitalistic force, but rather the chemistry and physics would in fact explain everything, but biological systems were just more complex. And so we didn't quite understand everything that we needed to apply the chemistry and physics. If you think about this in context, concepts like allostery or even protein structure, DNA structure, none of that was known in the mid-1800s. That wasn't until the mid-1900s, really, that those concepts started to emerge. And so something as simple as allostery, that would have been labeled as something more vitalistic because it wasn't understood at the time. Now, let's look at a more detailed timeline. So it doesn't begin at 1880. It does not, the timeline in reality doesn't begin here, but when we start talking about enzymes and enzyme substrate complexes, that's where I'm going to begin. So in 1880, a man named Wirtz introduced the idea of an enzyme substrate complex. And at the time, this was more of an abstract idea that he threw into a paper in passing, but he is credited as being the first to test this idea. Now, move forward a few years to 1897, and Edward Buchner, he performed a set of experiments that really represented one of the final nails in the coffin of vitalism. What he did was he took yeast, he killed the yeast, filtered out all of the yeast guts, and basically just captured the soluble components of yeast, particularly of the yeast cytoplasm. So therein, you would have found the enzymes necessary for fermentation. So enzymes that catalyze the conversion of sugar into alcohol would have been there in the cytoplasm of yeast. And so basically what he did was he very clearly killed those yeast. He used a high pressure filtration system to lyse yeast and then harvest their guts. And then what he did was he took the guts and treated with sugar, and he observed the formation of alcohol. And so there, Buchner, he actually won the Nobel Prize for this later. He very clearly showed that you could recapitulate the reactions going on in the cell in an environment where you did not have a living organism. So this was a real challenge to vitalism, but not the end of vitalism. Vitalism really held on, and in some ways you can still see its effects today. Now let's move forward another few years to 1902. A man named Brown, he proposed the idea of the enzyme substrate complex, and he did so to explain enzyme saturation. Now the thing that Brown mistakenly did, he was actually working under conditions with substrate in very large excess of the enzyme. Of course, we didn't really know what enzymes were or things like that, but his substrate concentration was very high. And so he was working under conditions wherein his enzyme was always saturated. And he actually thought that you had zeroth order kinetics. He thought that the substrate concentration did not impact the initial velocity. And it was because he was always working under conditions with his enzyme saturated. However, he did use this idea of the enzyme substrate complex proposed years earlier to predict the idea of the saturation effect. Okay, so this is kind of the groundwork, but let's move forward a year to 1903. There's a man named Victor Henry shown here. He looks particularly upset at me at the current moment. I feel like I should put my slide away so I can talk about him without the anger coming at me. But Victor Henry was a classically trained physical chemist. And what he wanted to do was apply his physical chemistry training to the study of an enzyme. And around this time, this is really what the field of enzymology was. It was physical chemists turning their training, their chemistry knowledge, to the study of biological problems. And ultimately, that is what led to the development of really enzymology, biochemistry as such an interdisciplinary field. Now, what Henry did, he focused on understanding the kinetics of the enzyme invertase in order to demonstrate that enzyme catalyzed reactions followed the laws of physical chemistry. And because of vitalism, this was a very controversial idea at the time. Now, why invertase? Well, you're going to see in a moment that invertase is an enzyme that catalyzes a reaction that would have been readily observable at the time using the instrumentation of the time. Okay, so invertase. Why invertase? I told you sort of why a moment ago, but let's talk a little bit more about that. So invertase was an enzyme that was very well studied at the end of the 19th century and the beginning of the 20th. The enzyme catalyzes the hydrolysis of sucrose into fructose and glucose. This reaction was one that could be readily observed. At the time, we didn't really have solid spectroscopy. We didn't have access to really robust UV-Vis spectrophotometers. And So, those instruments that were available were very time consuming for simple measurements, and that wouldn't have allowed for the observation of kinetic behavior of an enzyme such as invertase. So for that reason, what was used was polarimetry. In this case, the inversion of sucrose was easy to follow in a polarimeter. Sucrose is dextrorotatory, whereas the previous sugar that you start from, or rather anyway, you go from a dextrorotatory behavior to a levorotatory behavior. And so that was fairly easy to observe using polarimetry, which was something that was accessible at the time. So Victor Henry, what did he do here? Well, he studied the behavior of invertase using polarimetry. He observed this reaction. And Henry sort of built upon the proposal of Brown by extending the idea of enzyme saturation, though, again, it was not well appreciated at the time. But what Henry did from his data was quite interesting. So he actually noted that if you plotted the dependence of your initial rate on the amount of sucrose that had been added into the reaction, he noted hyperbolic behavior. However, if you look at his original paper, he did not give the curve, he did not plot the data, and he didn't, in fact, he did not even try to analyze his data. To be fair, it would have been quite complex. It would have been hard to analyze given the lack of computers at the time. But it is surprising because Victor Henry actually had 2 PhD degrees. There was one in psychology and one in physical chemistry. So you would have thought that someone that was intentionally trying to apply physical chemistry would have actually tried to do the data analysis. He did not do that. However, what he did do was write out the equation that we now call the Michaelis-Menten equation. He never actually used it though, but he predicted based on the equation that you would have hyperbolic behavior, which was consistent with his experimental data. It is unfortunate though that he did not actually try to use the expression. So flash forward another 10 years to 1913. A team of Michaelis and Menten, so Maud Menten and Lenore Michaelis. I'll tell you more about them in one moment. They approached the problem of the invertase kinetics and other enzymes too, but they approached the problem that really blocked Henry from going forward by making certain assumptions as well as the general application of an initial velocity style analysis. So this is important. Why would we really embrace the initial velocity approach? Well, there are 4 major reasons that you would want to do this. The first of which is simply that the complications of the reaction go away. And what I mean by this is, earlier I told you that if you let a reaction go for a sufficiently long period of time, you're going to see that product formation becomes nonlinear as a function of time at some point. So by focusing on those very early time points, as close to time 0 as you can get, you not only have linear formation of product with time, so there, by virtue of the fact that you have linearity, you also have a constant rate under those conditions, but also you don't have significant product accumulation yet. So product can feed back and actually inhibit some enzymes. And if you have a lot of product accumulating, you could see feedback inhibition occurring, and therefore you would see loss of catalytic activity as a consequence. There's also something to do, another factor that relates to the product itself in this case. So if you're talking about the enzyme invertase and its function, what can happen, so invertase will produce its products. Some of the products can undergo mutarotation as well. However, by focusing on those initial velocities, those initial time points, you are basically collecting data under time points that are too fast to capture that mutarotation. So mutarotation will be kinetically slower than the reaction that you're actually interested in. Also, because you are collecting data on very short time points, the reverse reaction can also be ignored. This is a reversible reaction. So as you accumulate product, theoretically you could have some flow back, some product convert back into substrate. And so by focusing on those very early time points, you don't have an appreciable reverse reaction taking place. Also, initial rate equations are simply easier to derive. They're easier to use than the integrated rate expressions that Henry tried to use in years earlier. Also, by virtue of working on those shorter timescales, you don't have pH drift, temperature drifts, you don't have baseline issues. So for these major reasons, Michaelis and Minton were really the first to not only generate data, but to analyze that data. And it's quite impressive if you think about the fact that they didn't have the computational resources that we have now. So really very, very impressive. Now, briefly, I want to give you an introduction to the people. So for those of you that are interested in the science, you can find the paper originally written in German. This is the title. It has since been converted into English in the early 2000s, 2010s. There was a man named Ken Johnson that translated their paper into English. So it's a very important paper, but let's focus on the people for a moment. So Michaelis, he was a fairly well-established physiologist in Germany at the time. So we're not really going to focus so much on him. He was a white male in Europe doing science, and his story is impressive. He was a very impressive scientist, but I think Maud Minton, her story is really just inspirational. So she was born in 1879 in Ontario, Canada. She aspired to be a medical scientist. She wanted to be really a doctor. However, she was born during a time when women were not allowed to do research in Canada, much less go to medical school or anything of the sort. So she wasn't discouraged by this. Instead, she went abroad. She went to the United States and Germany to do research. So let me give you a sort of a timeline here. She got her bachelor's in 1904. She actually got a master's in 1907, an MD in 1911, and a PhD in 1916. So in sum, she had 4 degrees. She was among the first Canadian women to even earn a medical doctorate. Now, I think this is very interesting. So what she did, she actually went across the ocean. She traveled in 1912, which for those paying attention, that's the year the Titanic sank. So pretty risky thing to do at the time. She traveled alone across the Atlantic to Berlin, Germany, just so that she could work with Lenore Michaelis. So she went to work in his lab for him, and together they developed the Michaelis-Menten equation. Now, this occurred fairly early in her training. She went over in 1912 and actually earned her PhD 4 years later. But she didn't stop there. She actually kept quite busy during her lifetime. So after attaining all of her degrees, she came back to the U.S. and joined the pathology department at the University of Pittsburgh. She also served as head of pathology at the Children's Hospital of Pittsburgh. It was not uncommon to find her working 18 hours a day, which is really, well, I don't do that. And that's, I find that very, very impressive. Not necessarily something I would want to emulate, but you can see sort of the philosophy that she is employing at the time. It's really one that, I'm a woman and I have to put in more hours and really work hard to get ahead. And that is more of a reflection at the time of the time. So altogether, I want to sort of make you understand that Maud Minton, when we talk about Michaelis and Minton of Michaelis-Menten, she had to work very, very hard, had to put in a lot of hours, travel across the world to not only gain her education, but to even get her foot in the door to do the work that her male peers were doing. She had 4 degrees. That should tell you something. So when we talk about Michaelis and Minton, just know that Minton is a very strong female role model here. I've already given you some of the assumptions that Michaelis and Minton had to make, but to further that, so they had to simplify their kinetic treatment in order to really do the data analysis at the time. And so they either explicitly or implicitly made the following assumptions. First, they assumed that during that initial rate phase, at those very short time points, that little substrate had been consumed and little or no product had been accumulated. So this is an important thing to consider, because if you assume that very little of your substrate has been consumed, you can also treat it as a constant. And for the most part, their substrate concentrations were in excess of their enzyme concentration, sufficiently so that the substrate concentrations could be treated as constant during their experiments, and you then didn't have to model the changes in substrate concentration as a function of time. You just say, oh, I have a lot of substrate, and it's enough to treat it like a constant parameter. They also assume that their total enzyme concentration remained constant, and that the total enzyme concentration reflected the sum of the free and enzyme substrate complex concentrations. Okay? They assumed also that the enzyme would interact with substrate rapidly, such that you could form an equilibrium that could be treated with an equilibrium constant. And I'm not going to focus too much on what this means just yet. I will in a moment. They lastly assume that the enzyme obeys saturation kinetics. So your saturation effect is in place here. You'll see how these come out in a moment. We can now turn our attention to a discussion of the actual chemical mechanism Michaelis and Minton put forth. Here, you're going to find some symbolism. First, when you see E, this references enzyme, S substrate. E plus S are going to come together. So enzyme is going to bind substrate to form enzyme substrate complex, here written as the ES complex. Now, this step is going to occur with defined forward and reverse rate constants. K1 is the forward rate constant, where this tells us how fast E and S come together to form ES complex. And K minus 1 is the dissociation rate constant, the rate constant describing dissociation of ES into E and S. Now, I want you to go ahead and take note here. K1, it is going to be a bimolecular rate constant. Here, enzyme and substrate have to come together, so two things have to come together to form ES complex. The reverse, the dissociation, this is going to be a unimolecular event, so a first order process wherein ES, one thing dissociates into two. Okay, so we can, based on knowledge of the forward and reverse rate constants, calculate an equilibrium constant based on the ratios of K1 and K minus 1. We'll get to that in a bit. The rest of the mechanism here relies upon knowledge of the chemistry. So here, ES is going to convert substrate, rather enzyme is going to convert substrate into product and ultimately dissociate into product and free enzyme. And this occurs with rate constant K2. So K2 here is assumed to reflect the chemistry, the actual chemical conversion step. Now, one thing I should point out is that this mechanism as presented is very general. And what I mean by that is certain steps are left out. For example, in reality, ES would convert to EP. So enzyme substrate complex would convert to enzyme product complex, and then product would dissociate. As shown, this has everything occurring in one step, where ES suddenly converts to dissociated product and enzyme, and in reality that is not realistic. So why? Why is that? Well, it's assumed that the chemical conversion step, the actual chemistry, is rate limiting here. And so it wouldn't really matter realistically how you write it out, because if chemistry is rate limiting, in practice you wouldn't be sensitive, your methods would not be sensitive or pick up those other steps. And so often this second step, this conversion of ES to free product and enzyme, is assumed to just be reflective of chemistry, and is also assumed that there is basically one slow step that limits the overall process. Now at this point you have free product, you have free enzyme. This enzyme can cycle back around and do the whole thing again. So this is the catalytic cycle that was put forth by Michaelis and Menten. Now there are some assumptions that we can make, or rather conclusions that we can make from this model. So the first of which is related to substrate concentration. Okay, so at low substrate concentrations, you're going to see, if you think back to our plots of reaction velocity versus substrate concentration, you're going to see a linear dependence in velocity on substrate concentration. But then when you get to really high substrate concentrations, you're going to see saturation. You're going to see that your initial velocity can't go any higher, and you approach something called the maximum velocity. Okay, so this should make a little bit of sense to you if you look at this. So when your substrate concentration is in great excess of enzyme concentration, it doesn't really matter how much higher in substrate concentration you actually go, because once you bind up all of that enzyme, you can't really go any faster. So mathematically, this should make sense. Conceptually, it should make sense through the lens of the saturation effect. Once you put a substrate in every binding site, you have no more binding sites to put substrate into. Therefore, it doesn't matter if you keep increasing the substrate concentration, you've already saturated all of your catalytic sites. So just try to keep that in mind. Now, I've gone through the rate constants and what they mean, but one other assumption that you're going to see in a second is that this is a true equilibrium process, that enzyme binds substrate to form ES, and that is truly reversible, and that this K1 over K minus 1, these forward and reverse steps, are reflective of an equilibrium that exists between enzyme substrate and ES complex. Now, once you convert substrate to product, this K2 step is assumed to be irreversible. So the actual chemistry step is assumed to be irreversible. That is, product cannot spontaneously convert back to substrate. Now you will find modified Michaelis-Menten mechanisms that are out there that do try to model in complexities like that, but in the simplest scheme shown here, we don't assume that. We assume that chemistry is irreversible and that enzyme substrate binding occurs as an equilibrium process. Okay, so we're going to start walking through a derivation here, and this is not meant to be scary to you. This is not meant to make you a math expert either, but what it is meant to do is to introduce you to the assumptions that are made in the derivation of the Michaelis-Menten equation. You're going to see this equation a lot, so it would help to understand where it comes from. So first, when we talked about initial velocity methods, I told you that it is often easier to observe product formation or substrate depletion as a function of time, as opposed to actually trying to observe intermediate species. And you'll see this will come back later, but here we're going to assume, based on that we are going to be detecting product formation. So enzyme will bind substrate, and then you'll see downstream a formation of product that should increase over time. Okay, so we can write out, based on the Michaelis-Menten mechanism shown here, an equation, a differential equation that captures the change in product concentration as a function of changing time. Now, under a specific set of conditions, this is basically what we measured when we went through the initial velocity methods. I told you, I showed you there an example of simulated data that I created where we simulated the product formation as a function of time, and in those time points that were very close to time zero, you had a linear region. Okay, so we took the slope of that linear region, and we then used that slope, that initial velocity, as a function of substrate concentration to ultimately determine the overall rate constant for the reaction. Okay, so the slope there, that would have been the change in product as a function of change in time. So dy over dx. That is all this is. This is just an initial velocity. It's a slope in your product formation as a function of time plot. So here we are looking at the formation of product over changing time, the slope of that. That is our rate of product formation. But we can write this out using rate constants. We can write out a rate equation. So when we do this, when we look at this overall mechanism, you should see here that product, here's your product term. It occurs nowhere else, okay? It also occurs with an irreversible K2 step here. So the only term that your product concentration depends on is the concentration of ES, and of course your rate constant K2. So if you write this out, your equation becomes K2 times ES, the concentration of ES, and there you go. So this is your rate equation for your product term. Now, we have a problem. The concentration of ES as a function of time, this is something that you can't easily determine. I mean, you can determine it, but it is not a straightforward process. So in this mechanism, when we talk about assumptions, one thing that you have to go ahead and account for here is that we can pretty readily monitor what goes in. So substrate, we can monitor the concentration of what goes in. We can monitor the concentration of what comes out. But the stuff in between, ES or other intermediates that may be present, we are going to have great difficulty monitoring that. So what we're going to do here in the math is put this equation into terms of things that we can easily determine. So we need to go ahead and derive an equation for ES that allows us to basically plug in and remove those intermediate terms. So what we're going to do, we're going to write out a differential equation. Again, this is just change in ES concentration as a function of changing time. We're going to write out a differential equation term for ES. Okay, so let's look at ES. Here it is. Okay, so let's first look at the steps that contribute to its formation. Okay, I only have one arrow that points to it. That's the K1 step. This is E plus S forms ES. Okay, so that would be a formation term. So let me write out my information for that. Okay, so that would be K1 times the concentration of E times the concentration of S. And that is what I have right here. Now, if you look at these two other arrows, they're pointing away from ES. So these are going to be steps that deplete the concentration of ES. Okay, so let's look at those. Okay, the first one, let's look at K minus 1. So here, this is a first order decay or decomposition that is going to lead to depletion of ES. So we can write this out as K minus 1 times ES, the concentration of ES. That's what we have here. You'll notice this is written with a minus sign because that tells me that the concentration of ES is decreasing over time. For that step, I mean. And there's also K2. So K2 times ES forms product. So that's what is written right here. This is another depletion step. So you should note that the overall differential equation for ES as a function of time is basically a balance of the formation versus depletion steps. That's all it is. It's just a sum of terms that balances formation and depletion. So now that we have this, there are some additional assumptions that we're going to make. I'll tell you about those on the next slide. We're going to make two major assumptions here. The first of which is that we're going to assume that the binding of substrate by enzyme to form ES complex that this occurs reversibly and ultimately forms or can be represented by an equilibrium. Okay, so this is not your standard equilibrium though, and you'll see what I mean by this in a moment. But when we write out the equilibrium constant, we can write this out as K minus 1 over K1, and this is going to be represented as a dissociation equilibrium constant. Remember, you can use the ratio of the association and dissociation, or reverse and forward rate constants, to define equilibrium constants. Okay, so having said that, K1 over K minus 1 would be your Ka, K minus 1 over K1 would be your Kd. So you'll notice here, this is written out as Ks. So Ks is a dissociation equilibrium constant, but what the S refers to is steady state. So here, you'll see in a moment that we make an assumption that the ES concentration maintains a steady state. That is, once you reach a certain point, its concentration basically is constant. It is in steady state. Okay, the thing to remember here is that a reaction that achieves a steady state is not technically at equilibrium. The concentration of substrate and product are rapidly changing, but the concentration of ES and your concentration of enzyme are essentially going to be constant. So when we write this out as Ks, we are writing out Ks to really differentiate this from a true equilibrium constant. So here we are determining an equilibrium constant based on something that is not technically at equilibrium. You still have a system in motion, but you are looking at this from the perspective of a pseudo-equilibrium constant. Now, if this is a true equilibrium, we have to make an additional assumption based on that, and that is K minus 1, this reverse step, is much, much, much larger than K2. So in order for this to be treated mathematically as an equilibrium, K2 has to be very small relative to K minus 1. This is what is referred to as a rapid equilibrium process. Later, when we start talking about some of the parameters of the Michaelis-Menten mechanism, you're going to see that this assumption is incredibly important, because otherwise, what you're going to have is a dissociation constant, so Ks, if you wanted to write that out, that would equal K minus 1 plus K2 over K1. And that is not a valid equilibrium constant. So by assuming that K minus 1 is very large relative to K2, the K2 term in essence goes away, and you're left with something that can be treated as an equilibrium constant. So just try to remember that here we make the assumption of a rapid equilibrium wherein K minus 1 is very large relative to K2, and this assumes that this binding of substrate forms an equilibrium complex. Okay, the second assumption here is that we are at steady state. And I've already given you some idea of what that means, but let's actually talk a little bit more about what it really means. If you look at a plot of concentration, this is concentration of substrate, product, ES, E, so basically all of these species, all of the different parts that occur throughout this mechanism, the concentration of those things as a function of time, you're going to see that at very early time points, you have a nonlinear decrease in the concentration of free enzyme, a corresponding nonlinear increase in the concentration of ES, also a nonlinear decrease in substrate, and increase in formation of product. But once you reach a certain point, all of that changes. So these early time points, this is something that's often referred to as the pre-steady state condition. So there's a lot of information there that can be had, but the Michaelis-Menten mechanism does not really deal with the pre-steady state. It deals with the steady state, which is why it is often referred to as a mechanism of, that really captures steady state kinetics. Okay, so what is the steady state? Well, you'll notice that beyond a certain point, substrate depletion is linear, product formation is also linear, your concentration of ES and free enzyme are fairly constant. They are just, they've plateaued. Okay, so this is your steady state. So it is referred to as steady state because basically the concentration of ES and free enzyme are unchanging over time, and product and substrate formation and depletion are linear. So when we talked about initial velocity methods, I told you that we would take the slope of time points that were very close to time zero, right? Well, herein lies a limitation of that. If you're too close to time zero, you have nonlinear behavior. So what you really want is to be close to zero, but not really that close. You want to be close enough that you have linear product formation, but not so close that you have nonlinear product formation over time. So from this, you should be able to take the slope of that linear region or of either product or substrate, and that would be your initial velocity. Now, under these same conditions, you have a constant concentration of ES and a constant concentration of enzyme. They're unchanging with time. If you let this reaction go long enough, what you're going to see is that ultimately you're going to run out of substrate. You're going to start to deplete your substrate to the point where your ES concentration becomes nonlinear with time again. Your free enzyme concentration also goes back up, but it's in a nonlinear way. And so this would represent basically the two time points that are too high. If you want to think about this as a Goldilocks analogy, you have time points that are too short, time points that are too long, and then you have the steady state region where everything is just right. Okay, so with that, why am I making such a fuss about the steady state part of this plot? Why do we care that enzyme concentration or ES concentration is constant with time? So first, let me remind you that when we write out the differential equations, we're always writing out basically an equation that captures the slope, this slope right here, the change in concentration of product, change in concentration of ES, enzyme, substrate, as a function of changing time. So if the concentration of ES and E are not changing, that is, they are zero, this is a flat line, what that then means is that my differential equations can be set to zero. Okay, so for ES, you'll see the change in ES concentration with changing time. If this is flat, this term actually equals zero. This is a very useful thing because I can then treat that differential equation that I wrote out in previous slides, I can set it equal to zero and treat it algebraically. So by assuming a steady state, what I have done is dramatically simplified my math. I don't actually have to use any calculus here. I don't have to integrate anything. I don't have to take derivatives. I can just treat it algebraically. I can set this equal to zero, rearrange terms, and then plug into my product rate equation. So that's what we're going to do. Now that we have the assumptions of the Michaelis-Menten mechanism taken care of, let's actually walk through the derivation of the Michaelis-Menten equation. Okay, so here's the mechanism, the chemical mechanism that we have already talked about. I'm not going to go through this one again because you've already seen it, but let's get back to where we were in our derivation. We had just written out a differential equation for the ES intermediate term. So we wrote that the change in ES concentration with changing time would equal K1 times E times S minus K minus 1 times ES, also minus K2 times ES, and that's what you have seen here. Now, if we assume steady state conditions, we know that this slope, this differential, equals zero, so we can set this overall differential equation equal to zero and treat it algebraically. Now, our goal here is to solve in terms of ES, which will then allow us to plug into that product differential equation that I showed you earlier. Okay, so if we do that, let's start moving some things around. We get all of our ES terms on one side of the equal sign and everything else on the other side. Okay, keep on doing this. And so here we have this, but I've also gone ahead and made a substitution. So here, this E that you see right here, okay, what have I done in this next step? Well, this assumes that you have free enzyme. If you look at the mechanism, you'll see that you have free enzyme, bound enzyme, and then again free enzyme. This term here, if we are going to use this in practice, it needs to reflect what we can experimentally determine. So what we really want is everything in terms of the total enzyme concentration, because that would then allow us to more readily use the equation. Again, it's hard to experimentally determine the concentration of free enzyme, or in fact intermediates, ES complex, during the course of an experiment. So what we're going to do is basically derive an equation that is in terms of the total enzyme concentration that you put in. So we've dropped in place of free enzyme, E total minus ES. Remember, the concentration of total enzyme is going to be the sum of free enzyme plus ES concentration terms. So if you take that, rearrange it, your free enzyme equals your total minus your enzyme substrate complex concentration. So that's what we have right here. So we've dropped that in, and we have a slightly expanded equation, but we can simplify. So we can do some simplification, work through this, and now you have the concentration of ES is equal to K1 times total enzyme concentration times substrate over K minus 1 plus K2 plus K1 minus, times substrate concentration. So this is an algebraically determined expression for the concentration of ES. Now I can take this a little bit further. I can simplify a little bit further. So what I'm going to do is multiply by 1 over K1, because remember, you've got K1 up here, you've got down here, so we'll just do this and simplify a little bit further, and that brings us here. So now our ES concentration equals ET, extraterrestrial, ET of course, times substrate concentration over a ratio of rate constants plus substrate concentration. Okay, so now what are we going to do with this? Well, we can take this and plug it back into the product equation. Again, here we have our ES equation. So let's take this, let's use it. Okay. So going back to our product equation, change in product as a function of changing time equals K2 times the concentration of ES. So we're just going to take the ES term that we've just solved and plug it in. That's all we're doing. That's what we have here. Now the product equation becomes a little bit more complicated, but we have things in terms of parameters that we can readily know. So let's simplify this further though, because this is not the prettiest equation as shown. Okay, so here's your term, your formula as laid out with everything plugged in, all parameters shown. But in reality, it may be difficult to actually deconvolute via steady state experimental methods all of these rate constants in one experiment, that is. So what people often do is they lump parameters together into what are called composite parameters. So as an example, you'll see Vmax written right here. Vmax equals K2 times your total enzyme concentration. That's what you were shown down here. So Vmax is a composite parameter. You can experimentally determine Vmax independent of everything else. Without any additional knowledge, however, you cannot deconvolute K2 from total enzyme concentration. That is, unless you know the total enzyme concentration. If you know that, you can then deconvolute the composite parameter into each of the individual terms. So the ratio of rate constants you see right here, this is what we refer to as Km, the Michaelis constant. So earlier when I talked about Ks, I mentioned that the equilibrium constant would include contributions up top here from K minus 1 and K2. So the Michaelis constant, under some conditions, if the rapid equilibrium assumption holds, can be treated as a Ks, or a steady state dissociation equilibrium constant. Okay, but additional information is going to be needed to really know whether that assumption holds. All right, so now you know what a composite parameter is, and also you've seen for the first time where the Michaelis-Menten equation came from. So that is what you're looking at right here. So you'll see in a moment that this is going to be a rectangular hyperbola. That is what the math predicts. And so you should take note of the fact that Vmax here more or less functions as an amplitude term. If you hop to what Vmax actually equals to, so K2 times your total enzyme concentration, what I want to go ahead and highlight is K2, it is what it is. But if you increase the concentration of total enzyme, because Vmax functions as an amplitude term, that means that the amplitude of your hyperbola is going to increase with increasing enzyme concentration. You'll see this play out in a moment, but I wanted to go ahead and plant the seed there. So first we're going to talk about the Michaelis constant, and then next we will talk about some other parameters that are related. Okay, so looking at the Michaelis constant, I've got it written out right here for you. Now, conceptually, all it is a dissociation equilibrium constant. So when we talk about dissociation constants, in the past, what I have told you is the Kd is equal to the substrate concentration or ligand concentration that gives you half saturation. So if you think back to fractional saturations, you had an asymptotic approach to 100% saturation, and then the substrate concentration or ligand concentration that gave you 50% saturation. If you extrapolated that to the x-axis, which is what is shown here, that would give you an estimate of your Kd. Now, in this case, you're doing exactly the same thing. So qualitatively, you're going to have an asymptotic approach to some maximum value, which is defined as Vmax, our maximum velocity. Knowledge of Vmax then allows you to calculate Vmax over 2, or 50% of Vmax. You can then extrapolate down to your x-axis to a substrate concentration, and qualitatively, that is going to be Km. That is your Michaelis constant. Okay, so qualitatively, that is how you would go about determining your Km. Now, at substrate concentrations below Km, you are going to see that you have first order kinetic behavior. Your substrate concentration is going to promote a linear increase as you increase the substrate concentration below Km. You're going to see a linear increase in the reaction velocity. But then as you get above Km, you're going to approach your plateau, and you're going to see a transition to zeroth order kinetics, such that when you are above your Km, you basically are, your rate, your initial velocity, it is independent of your substrate concentration. So that is really what you should see in this hyperbola. Now, I also want to go ahead and point you to the Km itself. Earlier, I told you that we assume that K minus 1 is much larger than K2. K2 is the chemistry step. K minus 1 is the ES dissociation step. And so you should see mathematically here that if that assumption of a rapid equilibrium, if it holds, if it is to hold, then your Km would approximate a dissociation equilibrium constant only if K2 is very, very small relative to K minus 1. If you think about how you would write out a KD, your KD would be written as K minus 1 over K1. But now you have a K2 term. So what do we do with that? Well, if K minus 1 is very, very large relative to K2, then we can assume the contribution of K2 is minimal, and this roughly approximates a dissociation equilibrium constant, a Ks term, a steady state dissociation constant. If the rapid equilibrium assumption does not hold, if K2 is larger than K minus 1, then your Km in no way, shape, form, or fashion approximates a KD. So this whole thing that I just told you, determining Km based on half Vmax, extrapolating to the substrate concentration and then treating that as a KD, that doesn't really hold if K2 is larger than K minus 1. So this Km can only be treated as an equilibrium constant, a dissociation constant, if K minus 1 is much larger than K2. Our next term that we are interested in is the rate constant describing chemistry. So thus far I've written this as K2, but this is more commonly referred to as Kcat, the catalytic constant. Okay, so we can determine this from knowledge of Vmax. If you know Vmax and you also know your total enzyme concentration, the ratio of those two things gives you K2, or Kcat as we will now call it. If I write out the product rate equation as we saw it before, remember K2, Vmax equals K2 times your total enzyme concentration. So this term here is Vmax. But K2 here, you could equally write that as Kcat. They're just symbolically represented. They're used interchangeably. So Kcat, it is your catalytic constant. It is sometimes called your turnover constant as well, because you can use it to calculate the number of molecules of substrate that are turned over per unit time. So Kcat here, you should see first, based on the actual kinetics, this is a first order decomposition. So your Kcat is going to have units of a first order rate constant. Okay. Now, we talked about Kcat and Km, but that doesn't really tell you the full story. It doesn't really allow you all of the information that you need to judge the efficiency of an enzyme. If you want to make comparisons between enzymes, this isn't the full story. You'll see why that is in a moment. But there's another term that we can use that is called catalytic efficiency. And the catalytic efficiency is defined as the ratio of Kcat over Km. So Kcat, the first order rate constant I just showed you, and Km, your pseudo dissociation constant. So the ratio of Kcat and Km gives you a number that has units of a second order rate constant. And it can be actually used to judge catalytic efficiency. So why? Well, okay, let me sort of step back here before I go further. Kcat over Km. Having a number that roughly approximates a second order rate constant would allow you to capture really the biggest event in what is often the limiting event, the E plus S goes to ES, that second order process, as well as conversion into product. So defining a pseudo second order rate constant using elements derived from the chemistry step as well as the binding step really allow you to compare enzymes. This makes it more of an apples to apples comparison, but there are limitations. So you'll see, first, the catalytic efficiency cannot be greater than K1. So if you are trying to capture binding as well as chemistry here, your catalytic efficiency can't be faster, can't be larger than the rate constant describing the complex formation in the first place. Your catalytic efficiency can't be greater than K1. You can't go faster than you could actually bind substrate. Okay? So the next assumption, or rather limitation, is that you also cannot, your catalytic efficiency cannot be greater than the diffusion controlled limit. So that number, that range is usually 10 to the 8th, 10 to the 9th per molar per second. And basically what you have here is a range. Your catalytic efficiency can't be greater than K1, but it also can't be greater than the limit that is set by diffusion. Two things diffusing through solution that are going to collide, basically that is your upper limit for how fast this can actually go. So enzymes with near perfect catalytic efficiencies that actually approach the diffusion limit, you can assume that they catalyze a reaction almost every time they encounter a substrate molecule. So if you have a catalytic efficiency that approximates the diffusion limit, you can assume that any time that two molecules, enzyme and substrate, collide, which is controlled by diffusion, that leads to a productive event that forms product. Okay, so let's actually look at these parameters for different enzymes. Here we have a table of different enzymes as well as their substrates, KMs listed, KCATs, and catalytic efficiencies. So what I want you to first see is that different enzymes have different KMs. And in fact, you'll see that chymotrypsin, for example, here you have 3 different substrates and there's a KM for each one of them. If your KM is an approximation of your KD, you would expect that different substrates would bind with different interactions, which would then lead to different KD estimations. So that is captured here in your KM difference. As you go down the column, you should also see that different enzymes catalyze reactions with different catalytic rates. In fact, chymotrypsin catalyzes with different turnover numbers or rates that depend upon the substrate as well. Okay, so we already see here that having different KMs and KCATs for different substrates, though for the same enzyme, would make it harder to compare enzymes with other enzymes. Okay. Now, we can compare on the basis of the catalytic efficiency. So you'll see that some enzymes are more efficient than others. Enzymes like acetylcholinesterase and catalase, as well as for fumarase here, they are near the diffusion limit. They are very near the diffusion limit. And so they are considered to be very efficient enzymes. Chymotrypsin, interestingly, its efficiency varies wildly based on the substrate that you give it. Okay. Then there are some enzymes like urease that are modestly efficient. One thing I do want to point out here, though. So I've already told you that Km, if you write it out, it is K minus 1 plus K2 over K1. So there's an interesting thing to note here. The apparent Km for the enzyme catalase, this would suggest pretty weak binding. This is actually about a millimolar, I guess 0.25 millimolar Km. That's fairly weak binding. And you'll see there's a very clear reason why. If you look at KCAT for catalase is very large. It's on the order of 10 to the 7th. If you independently determine K1 and K minus 1 for catalase, you will see that catalase is an example where K2 is larger than K minus 1. So catalase does not, the assumption of a rapid equilibrium there does not hold for catalase. So there, in your Michaelis constant, your Km, the K2 term is much larger than your K minus 1. So for catalase, your Km term, it does not approximate a Kd. So this term is meaningless in terms of binding affinity. And it is a very efficient enzyme, yes. That is very, very clear. But the assumption that Kd equals Km here is not valid for catalase. It is for many other enzymes where you'll see, for example, like chymotrypsin, your KCATs are much lower, fumarase much lower, but there are some enzymes out there that happen to be very, very efficient, and this then means that your binding affinity as estimated from Km is invalid. So there you have to independently determine all of those parameters. You have to independently determine Kd, you have to independently determine K1, K minus 1, K2, all of those things. Now that we have discussed the parameters themselves, KCAT, Km, let's talk about traditional ways to determine them. First, what I want to remind you of is that the tradition itself of how you would determine these begins in an era that predates computers, or at least computers sufficient to analyze nonlinear data. So much like the initial velocity analysis, where it was easy enough to determine a slope, here it is going to be mathematically much easier to take that nonlinear Michaelis-Menten equation and convert it into something that is linear. You can then plot it graphically and easily calculate your x and y intercepts. And so that's what we're going to do here. And before I do this, before I tell you more, let me reiterate that for certain parameters, like Vmax, for example, if you cannot accurately determine Vmax, that then allows you, or rather disallows you, from accurately determining Km. Remember, Km is the substrate concentration that occurs, or that corresponds to 50% of Vmax. So if you can't determine Vmax, you can't determine Km. If you can't determine Vmax, you also cannot determine Kcat, because Vmax equals Kcat times your total enzyme concentration. So Vmax is an incredibly important parameter, and you need to be able to determine it accurately. So in the early days of enzyme kinetics, in the Michaelis-Menten days, this was recognized, and it was, we needed a way to accurately determine Vmax, which would then allow for determination of other parameters. Okay, so these days, what we would do is just fit the nonlinear hyperbolic data computationally with ease. A rectangular hyperbola, this is an easy thing to fit in many programs that we have now. I can do this in less than 5 minutes. But in the days of Michaelis and Menten, this was not a straightforward thing to do. So what later occurred is that a series of efforts were made to take the nonlinear Michaelis-Menten equation and transform it into a straight line equation of form y equals mx plus b. So we're going to talk about some of these efforts here. The example that you are seeing here, you'll see that this is the most common representation, but there are other ways to go about this. This was a trial and error process that would ultimately lead to reasonable methods to linearly transform data and determine Km, Kcat. The first common method is the Lineweaver-Burke double reciprocal plot. This approach has errors, but is still perhaps the most widely used linearization method. So here you have a double reciprocal plot. You have taken the reciprocal of your initial velocity, so 1 over your y-axis, 1 over your initial velocity, versus 1 over your substrate concentration. So your standard velocity as a function of substrate concentration plot has just been replotted as a double reciprocal plot. So here the data become linear. You see that the slope of your line equals Km over Vmax, your y-intercept is 1 over Vmax, and your x-intercept is minus 1 over Km. So here, in one plot, you have a way to determine both Km and Vmax independent of one another, more or less. Okay, so the Lineweaver-Burke plot is very useful because it allows for straightforward determination of Km and Vmax, which are the parameters that we are ultimately interested in. But you're going to see that it has its issues. It has major issues with respect to how the substrate concentrations, the data points are distributed, as well as the error. So the two major disadvantages that I just told you, here, let's actually look at them for a moment. Okay, so first, let's look at the actual substrate concentrations. So remember, this is a reciprocal plot. So 1 over a large number gives you a small number. So here you'll see you've got some clustering of data points. You got data points that are not evenly spaced across the entire concentration range. So your data points down here reflect high concentrations, and your data point up here would reflect a low concentration. 1 over a small number would give you a larger reciprocal number. So here, the data points themselves are not evenly spaced, and you see that your higher concentrations of substrate are crowded all down here on the left-hand side of the plot. So this unequal spacing of data points is a problem. Okay, so that's one thing. But related to that, the propagation of error, think standard deviations or standard error measurements. The non-equal spacing of your data points based on concentration lead to very different propagations of error. And what I mean by that here is that small errors in your actual initial velocities will lead to very large errors in your reciprocal space. So you'll see here that, for example, your high concentrations here, your error bars are very low. But out here, your low concentrations, your error bar is very large. And that is not a consequence of there being more actual error in the experimental determination. This is how the double reciprocal plot, the Line-Weaver-Burk plot, actually propagates error. It propagates error unevenly across the concentration such that you have greater estimated error at low substrate concentrations relative to at high. And this is actually a very, very major problem of the Line-Weaver-Burk plot. You really want a plot that uniformly propagates your error across all of your data points. You don't want uneven, asymmetric error propagation. To address this issue of error propagation, the Haynes-Wolff double reciprocal plot was developed. So the Haynes-Wolff plot puts the substrate concentration over your initial velocity on the y-axis and plots that as a function of just your substrate concentration. So here you get a y equals mx plus b function that looks like this, where 1 over v max is your slope, your m, substrate is your x, and then your y-intercept here equals km over v max. So from the slope you can determine v max. From the x-intercept you can directly determine km. It's just x-intercept equals minus km. And this way of representing the data minimizes the odd, unequal error propagation you saw in the Line-Weaver-Burk plot. The Haynes-Wolff plot has the advantage of not overemphasizing data obtained at low substrate concentrations. So this is a fault that is inherent to the Line-Weaver-Burk plot. However, I will point out that both the Line-Weaver-Burk and Haynes-Wolff plots, they have a common advantage of allowing for estimation of both Km and Vmax, just simply through extrapolation of straight line fits, rather than having to estimate asymptotes. Now, you'll see if you go into the literature, there are many, many other ways to represent these data. You can take the Michaelis-Menten style rectangular hyperbola and transform it in a number of different ways. Edey-Hofstee plots are one example, Haynes-Wolff plots, Line-Weaver-Burk plots. These are all strategies that are meant to convert nonlinear data into linear data and ultimately, with time, hopefully address errors like, or rather disadvantages like uneven error propagation or clustering of data points like you saw in the Line-Weaver-Burk plot. There are a number of different ways that people have tried to address these issues. Even though we have just spent time talking about how the Line-Weaver-Burk plot has its disadvantages, it is still the most commonly used method out there to linearize the Michaelis-Menten data into something that is an easy straight line analysis. This is likely due to the ease at which you can take the reciprocal of your x and y axes, and you don't have to really think very hard. And so the Line-Weaver-Burk plot is still the most common method that is used if you're going to linearize your Michaelis-Menten or steady state data. So for that reason, let's actually look at an example. So this is an example of data that you might get. So here you put in different substrate concentrations, 1 millimolar, 2 millimolar, all the way up to 20 millimolar, and you determined an initial velocity for each one of those. So for each substrate concentration, you have a corresponding initial velocity that goes with that. Now you can plot this and you'll see that it is a rectangular hyperbola, but if you take the reciprocal of your substrate and your initial velocities and plot as shown, now you have linearized data. So if you just fit this to a generic y equals mx plus b function, that's what I've done here, you'll see that I get an estimate of my y-intercept, I get my slope, and from those I can calculate Km and Vmax. Remember, my y-intercept equals 1 over Vmax, so if I take 1 over this value, I'm going to get my Vmax, which is what is shown right here, 10.1 micromolar per second. That's based on the units that are shown up here. My x-intercept, which I can solve for here, equals minus 1 over Km. So as a reminder, my x-intercept is going to be found by setting y equal to 0 and then solving for x. So if I do that, my x-intercept I then get would be minus 1 over Km. And if I do that, ultimately my Km is going to be found to equal 3.1 millimolar. So it's got units of a substrate concentration. And so here, this is a representation of my KD. All right, so this is a rough example of how you would do this. And I want to go ahead and also point out, you'll see even here, the data points are not evenly distributed. You've got your higher concentrations clustered down here and your lower concentrations unevenly spaced out here. If you looked at the associated experimental error, you would see that it's overestimated out here and underestimated down here. So remember, these are major disadvantages to the Lineweaver-Burke plot, but you need to be familiar with it because it is still the most common route to determining via a linear transformation, determining Km and Vmax. We have spent a lot of time talking about steady state kinetics and what it can be used for. But we haven't really talked about its limitations as a whole. The biggest limitation of steady state kinetic approaches, such as those that we explored in looking at the Michaelis-Menten mechanism, is that we cannot use these approaches to unambiguously establish a reaction mechanism. Earlier, I told you that we can say something about the rate of substrate depletion or the rate of product formation, but what happens in between? We have no real way of getting at that information using steady-state kinetic approaches. So it's kind of like a black box. You can measure what goes in, you can measure what comes out, but you don't really know what happens in between. The example given to you here is that of a plumbing analogy where the pipes have been filled with water. You know how much water is going in, you know how much water is going out. You can relate that, water input, output via pressure measures, but you don't really have any information regarding where the water goes once it enters the box and basically, travels from the route in versus out. You don't know what's going on in here. This would require additional information like opening the box and tracing the pipes. The nature of your intermediates would not be measurable using the intact black box. The analogy I often like to use in this class is that of, I'm going to use a potty joke here. So imagine you are at a public event, a sporting event, a concert, something like that. And there is an intermission, halftime, some break between sets or something. You get up to go to the bathroom. Well, there's a line to get into the bathroom. And this is a case where for the guys, there's no urinals. Everybody's entering into a stall. So you walk into the stall after you wait in line, of course. You go into the stall, you shut the door, and you use the bathroom, you come out. Everyone that goes in enters and leaves at some steady state rate. When you get into the stall, you find, oh, the toilet paper dispenser, it's stuck or something, or the door latch is weird. Whatever it is, there is some act, some step of you going in, using the bathroom and leaving that limits the rate of everyone going in and out. So there is a rate limiting step that limits everyone going in and out. However, you, while you're waiting in line, or from the perspective of an observer, I don't know why you're observing people go in and out of bathroom stalls. That's kind of weird. But whatever the position of the observer, whether you're in line or elsewhere, you don't know what is going on in those bathroom stalls. You know the rate of people going in, you know the rate of people coming out. That's all you know. You would actually have to open the door, walk in, inspect, open up the black box, if you will, to figure out what is going on inside those stalls that is either slowing people down or making it possible for them to go in and out at the rate that they are. So here, getting back away from the potty humor to the steady state conversation, when we talk about steady state kinetics, we cannot unambiguously establish a reaction mechanism. That mechanism, in the example of the bathroom stall, the actual mechanism might be something like opening the door, closing the door, going to the toilet, pulling toilet paper, and then leaving. There's some order of events that the majority of individuals going in and out are going to adhere to. So in the black box strategy, you don't really know what the order of events are. You just know what is going in and what is coming out. And so here, in order to understand that, you have to apply additional experimental designs that are targeted at developing an understanding of what happens between the start and the finish. However, I will say before moving on that, as you're about to see, there are some details that steady state kinetic approaches can reveal regarding enzyme reaction mechanism. We're not going to have the full detail, but there is some amount of information that steady state methods can give you. To put this into a chemical perspective, I just told you that steady state kinetics cannot unambiguously establish a reaction mechanism. So in the example of the bathroom or the black box, you had a feel for what I hope you had an understanding of what I was trying to say. But in the sense of chemistry, here you have two different reaction mechanisms. And you can measure the rate of substrate consumption. You know how much substrate is going in both cases, in fact. You know how much product is coming out. You know the rate of depletion of substrate and the rate of formation of product. But steady state kinetics do not allow you to discern what is going on in between. So if it's a linear, ES goes to EX, goes to EP, goes to free product, okay? Or you have, in this mechanism, ES could go to EX or EY. Steady state kinetics do not allow you to discern one from the other. So that is the big point that I'm trying to make here. Steady state kinetics do allow for the discernment of certain overall reaction types. So here we're going to talk about some examples. The first is going to be the sequential reaction occurring via a single displacement. So first, reactions in which all substrates must combine with the enzyme before a reaction can occur and products to be released are known as sequential reactions. So here, what you're going to see is that there is a double displacement and a single displacement version of the sequential reaction. In the single displacement reaction, we have an example here. Your enzyme, you have a molecule PX and another reactant B. This is basically like a group transfer reaction. And what you are going to see is that basically the functional group X is going to be moved over to B to atom B to give you Bx as a product. So this is going to be what is referred to as a single displacement reaction and can occur via either an ordered or random process. So in the example of the ordered mechanism, an enzyme will bind to A to give the AE complex, and then B binds to give AEB. Both A and B are converted to P and Q, products P and Q, which sequentially dissociate until you get free E, which can then cycle around and do the whole thing again. So the ordered mechanism, the binding of the first substrate is apparently required for the enzyme to form the binding site for the second substrate, whereas you'll see here in a moment in the random mechanism, both binding sites are present on the free enzyme. So in the random mechanism, enzyme can bind A or it can bind B. No order is required as long as they both bind to form AEB, which then converts to products P and Q, and they dissociate randomly as well. So this is the ordered versus the random mechanism. So you'll see here that the assumption really relates to the accessibility of binding sites. In the ordered mechanism, as I just said, binding of A is assumed to induce a conformational change in your enzyme that generates the binding site for substrate B, whereas in the random mechanism, this is not an assumption at all. And so you'll see in a moment that we can use steady-state kinetics to discern the ordered from the random mechanism. In contrast to the single displacement reactions, we have a type of reaction that is referred to as a ping-pong reaction. This is a reaction that occurs via a double displacement reaction. In ping-pong reactions, the substrates A and B do not encounter one another on the enzyme. Many enzymes employ ping-pong mechanisms, and the math is a lot more complicated, but the basic fundamentals still are pretty accessible. So if you look at this, you'll see a mechanism looks something like this, where enzyme binds substrate A, so you have AE complex. A is converted to product P, but in the process, the enzyme undergoes a conformational change, which is indicated by the asterisk. So product P dissociates, and this newly transitioned conformation can bind substrate B, convert that to product Q, but in doing that, this basically resets the conformational state of your enzyme, and then Q dissociates and E can come back around and do it again. So the key here to note is that you have one or more products that are released before all substrates have been added. So substrates A and B are never bound to the enzyme at the same time. Okay, so this is important because this is what generally we refer to as a ping-pong or double displacement reaction. We can use steady-state methods to differentiate between the single and double displacement reactions. Okay, so this is all going to be, this is information that is going to be gotten from double reciprocal plots. What I want you to understand here is that each plot represents the increasing of your second substrate. So remember, this is a two-substrate reaction. Whether you're talking single or double displacement, you have a substrate A and a substrate B, or as is written here, substrate 1, S1, and substrate 2, S2. So imagine a situation where you do this reaction, you generate a single line, basically you do your experiment where you have your enzyme, you have a constant concentration of substrate S2, and then you vary the concentration of substrate S1. So that would give you one line. Now then imagine you come back and do the whole thing again, but at a different concentration of S2. That would give you another line. So basically what you're looking at here is a series of experiments, 4 experiments shown here, where in each case you are sampling the same concentration range of substrate S1, but you are doing this at controlled and different, systematically varied concentrations of substrate S2. Okay, so that then allows you to generate a series of linear, basically just lines, and you can determine Km's, Vmax's for each condition. Now, what I want you to go ahead and see here, and I'm not going to delve into the math, I just want this to be a qualitative look. Here, we can do this. We're looking for patterns. So what I want you to see is that in this case, all of your lines intersect. Okay? In this case, your lines are all parallel. So intersecting lines indicate that you have a ternary complex formed. So what that means is you basically have this ES1, ES2 complex shown here. In the case of the parallel lines, you have no ternary complex formation. You don't have S1 and S2 both bound to your enzyme at the same time. So here you should see pretty readily that we can discern the single displacement reaction from the double displacement reaction. But what I do want to highlight is that, or what I also want to highlight is that for the single displacement reaction where you have a ternary complex, the clarification of whether it is a random process or an ordered process is more challenging. So this does not tell you whether you have random or ordered catalysis. It just tells you that you have a ternary complex that forms. So here you can use steady state kinetics to differentiate the single versus the double displacement reaction on the basis of whether you form that ternary complex or not. So that has been an introduction into enzyme kinetics. And the reason that we focus so much on the enzyme kinetics here is that these parameters, Km, Kcat, catalytic efficiency, they really serve as the foundation for understanding how enzymes work. And when we start talking about enzyme mechanism, they are also the bedrock of figuring out, as you just saw, single versus double displacement reactions. Next time, we will turn our attention to a discussion of inhibition, which is a particular clinical significance. When we talk about developing drugs, those drugs are usually going to target some protein or enzyme in a cell and either stimulate its activity or inhibit its activity, modify the activity in some way that hopefully is going to lead to some clinically useful outcome. Now, understanding what type of inhibition is occurring really centers on the trends that you see in Km and Kcat. So the point here is to really develop your understanding of the basic Michaelis-Menten mechanism, and then next time we will see how that plays out in practice.